Welcome back to the type system. I'm Daniel, and in this video we will explore another powerful language construct in the form of self-types. So as is our little custom, we will do a new Scala application under the part 5 type system package. So let's call this self-types. Make it an object and also extends app. So what are self-types? Self-types are a way of requiring a type to be mixed in. Let me show you what I mean. I'm going to show you best by doing an example. So let's say we want to design an API for an awesome music band in which every singer must also know how to play an instrument. So we want to enforce this constraint. So if we have a little trait called instrumentalist, okay, and this has a small method play which returns unit. So this is the kind of guy or girl that can play an instrument. I'm definitely the kind of guy that plays guitar, okay? And say we want in our awesome music band that a trait singer must also know somehow to play an instrument. We can enforce that at the language level by saying, here's what I'm writing: self : instrumentalist arrow, and in the rest of the body I can define some methods like sing, for example. So this is a marker at the language level that forces whoever implements singer to implement instrumentalist as well. So note that this seems like a lambda syntax, but it means something completely different. So this is a new Scala feature that we haven't seen before in this course. So how is this useful? For example, if I have a class called lead singer, which is something that you have in a music band, right? So if this extends singer with instrumentalist, and we override, say, play and sing, then this is a valid extension because the lead singer extends the singer trait and the instrumentalist trait, which follows the constraint enforced by this construct. So this is again a marker that tells the compiler that whoever implements the singer trait must also implement the instrumentalist trait. So for example, if I have a class called vocalist which extends singer, then this would be illegal, even if I implement or override sing. This is still illegal because notice what the compiler says: illegal inheritance, self-type vocalist does not conform to instrumentalist. This construct is called a self-type. And the name self is just a suggestion. You can name it A, you can name it Scala, you can name it even the keyword this. So this whole construct here is completely separate from the rest of the implementation or API. Okay, so this self-type constraint here basically forbids us from extending singer without extending instrumentalist as well. So this is illegal. Let's see what other constructs are legal under the self-type. So say, for example, I have a value called James Hetfield with no connection to the Metallica lead singer, all right? So this is a new singer with instrumentalist. Okay, you can define an abstract type like that and instantiate it on the spot. So if I override the play and sing method here, then this is a valid assignment because James Hetfield is a singer and it mixes in the instrumentalist trait, which satisfies the self-type constraint. Another possible construct is if we declare a class. Let's call this guitarist, which extends instrumentalist. Okay, and we override play inside. Let's say, for the sake of variety, that this prints some guitar solo or guitar tabs for guitar enthusiasts. All right, and if we instantiate a value, let's call this Eric Clapton, amazing guitarist, equals new guitarist with singer, and we override sing on the spot, then this is also fine. So we've seen a few use cases where this trait singer with a self type is actually fulfilled in practice by instantiating types which are both singers and instrumentalist. Nothing less than that will be passed by the compiler. Now, a question that I often get asked is, Daniel, why do we need this special requirement syntax? Why don't we just say trait singer extends instrumentalist and be done with it? Well, we can of course make singer extend instrumentalist, but that wouldn't make too much sense because the concepts themselves are not related. Instead, we want singer and instrumentalist to be two separate concepts, and for our special use case, because we are assembling a rockstar band, we can enforce some type constraints on our use case. The question is legitimate because often self-types are usually compared with inheritance. So if I say class A and class B extends A, then B must also be an A, right? But when we say, by contrast, trait T and trait S, for example, with a self-type T arrow, then instead of saying that S is a T, which was the case with inheritance, we are saying that S requires a T. So this is basically saying B is an A, and this is saying that S requires a T. In other words, the trait S cannot be implemented without mixing in T as well. So T must be part of the equation of whoever ends up implementing S. So as you see, two very different concepts. Now, self-types are used in what's commonly known as, I'm going to write this down, as a cake pattern. This is Scala's equivalent to what in the Java world is known as dependency injection. Not only in the Java world, but oftentimes in the Java world. Now, this is a dependency injection because with a self-type, we enforce the dependency on a type, which will then be subclassed or quote-unquote injected later. That's why I put in the dependency injection in between quotes here. And the name of this pattern is the cake pattern because these dependencies create kind of like layers of abstraction, which get implemented at the very last stage of the code, which is often compared to baking a cake. So, as an example, as a general example, the dependency injection in Java, which is most popular, but like I said, also in other languages, we would write something like class component, right? So this is kind of a reusable component, and we write some code here or some API. And we write a class called, let's say, dependent component, which relies on a component injected as a value in the constructor. So val component of type component. And this is, of course, subclassed by, say, class component A, or a concrete component extends component, and many other classes like component B and stuff like that. And this dependent component at runtime can receive either of these components to compose our application. Now, in the dependency injection frameworks like Spring or other pieces of code, these components, these instances of the concrete components, are injected by the framework for us at runtime, depending on configuration we've set in some configuration file or from some other settings. Okay, so this is classical dependency injection. Now, in Scala, we write the cake pattern as, let's say, trait Scala component, and again, some API. And instead of passing instances of this Scala component as an argument to constructor, we can enforce the types by saying Scala dependent component with a self type. Self Scala component. So basically, whoever implements the Scala dependent component trait must also implement some form of Scala component. So say, for example, the API had a method called action on some int value and returns a string, then I'm free to use this action method inside Scala dependent component in some other API, like dependent action on x, which is an int, and it returns a string. And in this implementation, I can say action of x plus this rocks. Self-typing this allows me to call the action method from the Scala component as if it were my own. This works because the compiler knows in advance that whoever implements Scala dependent component must also implement Scala component, which of course has access to the action method. To give you an example of how the cake pattern would create abstraction layers, say for example that you are a backend developer for a server-side rendering app that displays some profiles and some dashboards, okay? So you would have to model how various elements on the page or in your front end would look like on the back end. So here goes a layer 1 with small components. Like, for example, a trait called picture extends Scala component. A trait called stats, which extends Scala component for whatever dashboards you want to say, and so on and so forth. So the small components would look like this in layer 1, each with its own API. Then at layer 2, you would start to compose components by saying a trait, let's say profile, or some other user profile or something like that, extends Scala dependent component with, and you can choose now which small component you want to mix in. For example, you want to mix in picture. Then say you want another big composite component, saying trait, for example, analytics, extends Scala dependent component with, say, stats. The point is, at each layer you can choose what components from the previous layer you want to mix in. Say, for example, you had a third layer with a trait, say, Scala application, with a self-type, which is a Scala dependent component, and with another API. Then you could implement this layer 3 at even a higher level and saying trait analytics app extends Scala application with, and you can then choose which composite component you want to use, say analytics, and so on and so forth. So you can bake your application in layers. The difference between dependency injection and the cake pattern is that at dependency injection, the framework or some other piece of code takes care to verify or to inject our values at runtime. Under the cake pattern, these dependencies are checked at compile time. So a fundamental difference. Now, one last tiny bit that I want to show you. The self-types allow us to define seemingly cyclical dependencies. Let me show you what I mean. So if I say, for example, a class, let's say x, and a class y extends x, and if I make x extends y, then that will be a cyclical dependency. This thing would not compile, because we have an illegal cyclic reference involving x and y. But with self-types, this is apparently possible. Let me show you how. Let's say I have a trait x that requires some trait y be injected. So I can say self y arrow whatever, and in the trait y I can say self x arrow, and this code will compile just fine. So weirdly, no complaints. But this cyclic dependency is only apparent because we're only saying, hey, whoever implements x must also implement y, and whoever implements y must also implement x. But there's no contradiction there. Basically, we're saying that x and y are unrelated concepts, but they go hand in hand. They're like sister concepts, if you want. As an example, we can think of a super music band that requires every instrumentalist to also be a singer. So, an important concept and a powerful Scala feature in this video. I'm Daniel, and I have more type system magic coming up for you in the next video.